Welcome again, everyone. This is Karen Hauk from the University of California at Berkeley. It's Solar Week this week, where solar scientists will answer your questions about the sun and life as a scientist, and that's at www.solarweek.org. We want to welcome our Solar Week webinar featuring Dr. Pat Reiff. Pat's a space plasma physicist from Rice University. And with the dawn of the new solar cycle we have starting now, solar activity is picking up. Although the disasters of the show Cobra are not likely to occur, it's gotten folks interested in the effects of space weather. This webinar will last about 30 minutes, and you're encouraged to ask questions along the way. We'll have to end right at the end of the 30 minutes. Again, your microphone is muted and your webcam is off. You can ask a question in the Q&A box throughout the webinar. Move your pointer, your cursor around, and the Q&A box will pop up. You can also ask questions of the solar scientists at www.solarweek.org through the end of the week, which is tomorrow. A little bit about Pat. Pat has been involved in space plasma physics research for over 49 years. She's participated in 6 NASA missions, starting with Apollo. She's currently the co-investigator and education lead for the Magnetospheric Multiscale Mission, which we call MMS for short, and was launched on March 12, 2015. She has led educational programs since 1988, including 4 in collaboration with the Houston Museum of Natural Science. Millions of learners have benefited from software, planetarium shows, web pages, and museum kiosks that she's developed, and has reached hundreds of thousands of learners in person. Welcome, Pat Reiff.
Great. Well, thank you very much. It's wonderful to be here, and I will share my screen, and hopefully we can get started quickly because there's way too much for me to say in a short amount of time. What happened very recently is a show has come out on PBS, and it's called Cobra. And it has Cobra has space weather as a plot device. And so it seemed like the appropriate time to kind of look at what it says and see if its science makes sense. Well, the first thing, of course, is what is space weather? Space weather isn't Earth weather seen from space, like this Hurricane Ike that hit us a while back. Space weather is not weather on other planets, like the Great Red Spot at Jupiter. But instead, it's how changes in the sun affects the larger environment of the Earth, mostly the magnetic field around the Earth, but also the ionosphere. And because it affects the ionosphere, it can affect communications and electrical transmission lines. So the question is, what can happen during a major solar disruption, and is the show Cobra realistic? Well, it's a UK-made disaster movie that uses a major solar storm as a plot device. I should say it's not suitable for under 14, but the strong language is bleeped out in the PBS version, and you can watch the first episode free on PBS. And I should say that most of the science is actually in the first episode, and the rest of it is just cleaning up the mess. Okay, so how realistic is it? Short answer is it's actually pretty good. The science is really quite good, but the consequences are really worst case and probably not what we would expect anytime soon. But, what do you expect for a disaster movie? All right, so Cobra stands for the Cabinet Office Briefing Room A, where all the cabinet gets together in the UK if there's a major event. And in the first briefing, the scientist, who's this guy here, and the science liaison officer to the cabinet, who's this guy here, warn the committee that there's a big major sunspot group coming around on the east limb that they're worried about. And he presents the point that it could flare in a big Carrington-like event that could cause both stage 1 prompt effects and stage 2 delayed effects from the plasma launch. I love the way they rename all these things to make it digestible. So they called it a plasma launch, which would be worse if the plasma had a southward magnetic field. Well, because at this point it was still several days away, the cabinet really didn't move into action. Well, so the question is, what is the Carrington effect? The Carrington event happened in 1859. Carrington himself observed a huge white light solar flare, followed less than 18 hours later by an enormous geomagnetic storm. And he was really the first one to put it together that the flare and the storm were actually related to each other. They'd had both of them, seen both of them before, but didn't really know that it happened. Well, what happened in Carrington, there were auroras. The northern lights were visible as far south as the Caribbean. The telegraph lines were impacted. There were electrical currents on the telegraph lines. Some of the telegraph offices actually caught fire. Some of them, they used the electricity in the Aurora to send their telegraph messages. They didn't even have to use their own batteries. So there's a nice little YouTube video on the Carrington event. Well, the question is then, could a Carrington occur today? The sun's been relatively benign over the last few years, but in fact, in 2012, there was a very big event on the sun that sent this giant burst of plasma, which we call a coronal mass ejection, away from the sun. But fortunately, Earth was here, and so it wasn't headed toward Earth. So we didn't get it. But stereo A, that was in the right position to see it, actually measured the plasma going past it. And there have been a lot of papers on this event, and there's a really, again, a nice YouTube video of Dan Baker's talk, the link there. A lot of people have predicted what the event would have happened if it happened at Earth, including mine. So what happens when you have a big sunspot group, and this sunspot group is getting more and more complex, and the sunspots themselves are getting larger and larger, and they come rotating in from the east side, when they stop and they're sort of right in the middle of the sun, that's when they're poised so that if there's a flare there, it can launch a particle blizzard our direction. And in fact, what happened in this Halloween storm and also in March of '89, there were two sunspot groups sort of following each other. And if you have two sunspots in a row flaring, then the results are a lot more dangerous, because the first one, the CME for the first one opens up the magnetosphere, and the second one can send in energetic particles. So having two in a row is even more disastrous. Okay, so anyway, the sunspot group can result in a bright flare, and that releases both visible and invisible light, and a blizzard of energetic particles. So this is a video of some a flare actually happening here, and you can see how bright that part of the sun is comparison to the rest of the sun in that wavelength, and it's significant. So if you're looking at the sun through a solar filter, or at evening or morning when it's relatively safer to look at the sun through when it's setting, then you can see these with your naked eye as white light flares. Okay, but when those happen, they send out energetic particles, and they can also send out coronal mass ejection. Okay, so a flare that occurs on the edge of the sun, like the ones we just saw, will launch a coronal mass ejection out to the sides. And these are very lovely, but they're not heading toward Earth, and so they don't have any effects on the Earth's space weather. But if there's a flare near the center of the sun, then it sends both the energetic particles from the flare, and it also launches that coronal mass ejection, that big plasma bob, toward the Earth. And it's called a halo CME. You see how it appears to act like a halo around the sun? That's because it's approaching us as it's expanding. That's the old joke is, I saw the baseball getting larger and larger, and then it hit me. And then that's what happens when it's coming straight our way. It gets larger and larger because it's heading right at us. But the other thing you notice is this snow. And this snow is the actual energetic particles from the sun hitting the detectors on those cameras and causing those detectors to light up. They're not designed for cosmic ray detectors, but they become a cosmic ray detector. And that's part of the problem with these cosmic rays. There's a lot of electronics that's not designed to respond to them. In fact, responds to them sometimes in a bad way. Here's another halo CME from another event from the larger field camera. And again, you see it expanding and you see the blizzard. This arm that looks dark here, that's actually like a popsicle stick with a disc on the front, so it blocks out the main light of the sun so that we can see the more dim corona around it. And again, you see the snow from the energetic particles. And this is a composite then of the sun's image, the inner corona and the outer corona from these Halloween storms. So there were some that went off to the side, but the big blasts are coming and come straight toward us. Bam. And I should say this movie and several others are in my space weather software that I'll give you the link that you can download it for free on our website. So when you see this blizzard of energetic particles, these can cause harm to astronauts. They can affect spacecraft and aircraft electronics. It can make GPS be wrong by 100 meters or more. It can impact radio communication on Earth. And in fact, there was a big flare occurred in August of 1972, which is my very first paper was about the effects of the August 72 event, and it would have killed the astronauts if there had been an Apollo mission at that time. And the problem, of course, with these energetic particles is there's essentially zero warning time. They travel at the speed of light, so when you see them, you're in them. So in Cobra, this prompt energetic particles causes the airport, the GPS landing path at several airports to have failed. So one of the planes was diverted to England and its avionics failed and it ran out of fuel and it crashed on the freeway. And I should say most disasters really take more than one failure to be a problem, to change it from a problem to a real disaster. And in fact, one of the cool things they did for this movie, they actually took an actual airplane and cut it up and spread it over the freeway to make it realistic. So then what happens? The phase two, is it going to hit? The CME only arrives in 1 to 2 days later, because this is now traveling. It may be traveling fast at 1,000 to 2,000 kilometers per second. But it's still a heck of a lot slower than the speed of light. So the speed of light stuff comes in just 10 minutes, but the CME takes a couple of days to get there. In the case of Carrington, it was only 18 hours. But when that CME hits the Earth's magnetic shield, it puts energy into the magnetic field, which ultimately powers the Aurora. And the stronger these events, the stronger that Aurora will become. And when you get a really super event like the March 1989 event, the Aurora, instead of being a relatively narrow ring near the pole, expands out really tremendously. This was an image from the March 89 event taken from the polar satellite. It was actually taken over the southern hemisphere. So here's Antarctica, and this is one of the few times that the Aurora Australis was actually seen in Australia and Tasmania, because the auroral oval had expanded so much. They mapped it to the northern hemisphere. So this is what that global aurora would look like if we had a satellite such as Polar above the Earth's northern pole at that time. So the ring of the Aurora was going roughly across the U.S.-Canadian border, but there was auroras predicted from this, even in the Carolinas. And if you now look at what the DMS-P satellite saw at that same time, now it only does a strip So an hour and a half later, it does this strip, and then an hour and a half later, it does that strip. But if you kind of put them together, you can see that aurora really along that U.S.-Canadian border, just exactly like Fuller said it would be, and these lower latitude auroras here. So when you get these huge auroras, it allows electrical currents to flow horizontally. Those horizontal currents can induce currents in the transmission lines, and this led to a huge blackout in Canada, and much of Quebec province was out of power for 8 hours that time. And so one of the things that can happen then is with these big induced electric currents is you can fry your transformers. And they asked in the show, what can happen? And he says, yeah, here's our transformers. They can blow if they get too much current through them. And transformers aren't small, and we don't have a lot of spares. And that is really true. These transformers are huge because they are changing the voltage from high voltages on power transmission lines to modest voltages so you can actually use them in buildings. So that was from the show, but in real life, here's a transformer that was fried in Massachusetts from that same event in March of '89 that I just showed you the aurora from. So these transformers can melt, and there were in fact transformers that failed even as far south as New Mexico. Okay, so Cobra says, we only get 30 minutes warning to know if the field is south when it passes our spacecraft at L1. Well, that's also true. We have our monitoring spacecraft are parked upstream at the L1 point, which is about 1.5 million kilometers, 1 million miles from Earth towards the sun. And that's a stable orbit. And so we put our solar wind monitors there. And when that solar wind passes that monitor at L1, then we know exactly how bad it's going to be. And more importantly, is that magnetic field going to be southward? Because it's a southward direction of the magnetic field that allows the energy from the solar wind to come in. We're protected from the solar wind by the Earth's magnetosphere, but our magnetosphere points north at the day side. And if the magnetic field of the sun is southward, these two fields can annihilate each other and can allow energy to be transferred in from the solar wind to the Earth. And these field lines open and get stretched out into the magnetic tail. And then when they snap back, we got magnetic disturbances and strong auroras. So what happens right at the end of the first episode? He says, oh, we're expecting to get our data in from L1 any moment now. And, you wait for 30 seconds. He says, the data's in. And sure enough, it's hot south. In other words, the magnetic field in the CME is southward, and so the big storm is coming. And again, that's correct. Once our monitoring spacecraft detect the CME, then we go from being on a sort of not sure how big it's going to be, but to being pretty accurate in how we can predict it. And then these storms will last anywhere from 8 hours to 36 hours, depending how strong the storms are. Here's an example of some space weather predictions that I do based on measuring the solar wind. The blue is what we predicted, and the red is what happens. So you can see we do a pretty good job of predicting how strong the storm is going to be. And here is 1 day. So the beginning part of the storm only lasts a few hours, but the extension can last more than a day on these really, really strong storms. And our predictions are only 1 to 3 hours in advance. And here's what we predicted to happen from this Carrington that didn't come our way, a much, much stronger storm if that 2012 event had come to us. Okay, so what is magnetic reconnection? It's the process where magnetic fields annihilate them on both sides, and it releases energy, and it accelerates plasmas in both directions. And by having 4 spacecraft go through the side of magnetic reconnection, you can really unfold the temporal and spatial variations of what happens in that process. And it's the MMS mission that's flying right now that is unlocking these mysteries. And we've really found over the course of this first 5 years of our mission some really amazing reasons why reconnection works. And I don't have time to go into it today, but suffice to say, it's a really fascinating mission, and there's a lot of really good ways you can learn more about space weather. Spaceweather.com is a great source of real-time information. My MMS.rice.edu gives the real-time space weather forecast. And if you go to mms.rice.edu, you can watch for free our show on magnetism, and download our free space weather software that has both a lot of the images that I'm showing here, and also real-time images of the sun in various wavelengths, so you can see how the sun's magnetic field is changing and what our predictions of space weather are going to be. So at that point, I will stop because I know we have a hard stop, and have some questions.
One question I've seen is, why is it important to predict space weather? I guess so that you don't have those effects that Cobra shows, but in the real world, what is the importance of predicting space weather?
There really are radio blackouts associated with space weather. And one time when President Nixon was on his first trip to China, when he was over the Pacific Ocean, he was out of radio contact for 4 hours, Air Force One. And, that's really scary. Having astronauts in space is an issue, especially if we want to go to Mars and have them exposed to space weather for 3 or 4 months of travel time to Mars and 3 or 4 months back. There are ways you can shield and get inside a watery packet hidey hole. Basically, you can make a cocoon out of water bottles and protect yourself from some solar energetic particles. But again, knowing when they're coming and what's likely to happen can help save astronauts' lives.
So you can literally wrap yourself in a bunch of water bottles for protection.
Yeah, what's interesting, the energetic particles from the sun, you can shield them with about 1/4 of an inch of aluminum, which is kind of heavy to do a whole spacecraft because most of them are not that thick, or 4 inches of water. So if you had, and you've got water on your spacecraft, so if you created a hidey hole that just uses your existing water packs, but in a cylindrical space that you can then dive into, then you can reduce the effects of that ionizing radiation. Interestingly, however, the galactic cosmic rays, the cosmic rays from the Milky Way, are so much more energetic that 4 inches of water doesn't cut it. And so, in fact, it's actually safer to go to Mars at times of solar maximum when the solar wind itself keeps the galactic cosmic rays out. And so you can shield against the solar ones, but you can't shield against the galactic ones. But the solar wind, when the solar wind is blowing strong, it protects us. And in fact, you can go on right now and look at the Coronal real-time videos. You can see the cosmic rays now because we're at such a low solar wind. Normally, you won't notice the galactic cosmic rays on the SOHO images because there's so few of them.
I see. Huh. Good to know. All right, let me look for.
Why was it called a Halloween storm? Yeah, because it happened on Halloween. There was one that happened on the July 14th, so they called it Here's
one. Who is responsible for predicting space weather and getting the alerts out to people?
That is an excellent question. NASA does predictions. I do predictions, but the official predictions come from NOAA. Okay, so if you are a power company and you want to know how to protect yourself, then you subscribe to the official predictions from NOAA.
So NOAA is the National Oceanographic and Atmospheric
Association. Yeah, and their forecast center is in Boulder, Colorado.
Yeah, been there. Cool place. I think you mentioned this, but when do the effects of space weather show up on Earth?
Well, the prompt one comes at the speed of light, but the effects of the CME happen a couple of days later, when that big blast of plasma from the sun hits the Earth, and only if it's coming our direction will it hit the Earth.
Let's see. Do scientists expect a huge solar storm as we're heading into solar max?
There will always be strong storms. Okay, like the one I showed you. It was a strong storm. We get a couple of strong storms every solar cycle. And we got lots of modest ones every solar cycle. But these horrendous big Mother Carrington events may only happen once every 100 years or so. And, so we don't know. It could or it couldn't. But like a lot of things, I live in Houston, and, we have to be prepared for a hurricane to happen anytime, because we had 4 this year.
Well, it seems like 2020 would be the year for something to happen, doesn't it? Based on everything else. See, is there any questions?
I will say I have a picture behind me of Shannon Walker when the space station, and I'm not a NASA person, I'm a Rice person, but she is in Crew 1 that's getting ready to launch in just a few weeks, and is a close friend of mine and an alum of Rice University. So
that's so cool.
Godspeed, Shannon. We are looking forward to your being on that big rocket.
Yeah. Let's see, we probably have time for 1 or 2. How are
I'll tell you a funny story.
Go ahead. Yeah, please.
If you don't have it. One of our secretaries was looking at the sun right at sunset one day, and as it was setting, you can see it because they're looking through a lot of atmosphere. It looks red. Okay, she saw a naked eye CME, and she sent me an email. She said, "What did I just see?" I went and looked at the solar data, and she did. She saw a naked eye CME.
Wow, that's pretty astonishing. Okay, I'm looking at the time, and I see we are about to end. Pat, thank you so much for coming today. I'm sure that people will come up with other questions, which you can ask at www.solarweek.org.
Quick one: how often do solar storms hit Earth? And the answer is little ones all the time, big ones less often, like asteroids. The big ones are going to happen very, very randomly, and the little ones happen all the time.
Well, it keeps life exciting, doesn't it? All right, Pat, thank you again. Happy Solar Week.
Take care.
You too.